All right, it is just after 1:30 in Saskatchewan, 3:30 where our presenters are from. So we are going to get started here. Just double checking that I am not muted. Perfect. So my name is Mercedes, and hello to everyone joining us on Zoom and joining us live streaming right now. I'm an education coordinator from the Canadian Light Source, and today I have the honor of introducing our group, which is the first group I've ever gotten to work with for students on the Beamline experience. Today I'm on my own as my teammates Dallas and Tracy are not here, but I'd like to give them a huge thank you for helping with the students on the Beamline project as I was learning and navigating my way through this new process, and especially after we switched to doing it virtual style. So thank you to my team. I'd also like to thank the CLS mentor, our science mentor, who worked with these students throughout their project, Jay Dines, who was a huge help, and especially with the data analysis aspect. And another thank you goes out to David Muir, the Beamline scientist, who helped with the virtual beam time and our data collection. So thanks to you guys. Today, our Students on the Beamline seminar is brought to you by Unionville High School. They are from Markham, Ontario, located on Treaty 13 territory. Just a couple of housekeeping items to mention. We are live streaming on YouTube, so this is being recorded virtually. So participants who are in the Zoom call, you're more than welcome. Please keep your video off if you so desire. I'm going to be spotlighting the students. And those of you, you may have some different viewing options while you're on the Zoom call, but you can pin the speakers if you'd like to see, and I'll be spotlighting the students, like I said. And if you have any questions for the Q&A afterwards, you can either type them in the Zoom chat. I believe there's also a chat on the live stream on YouTube. I'm not 100% sure, but I'll check that out. So you can type those questions in or raise your hand if you're on the Zoom call, and I will call on you to ask your question to the students. So with that, I would like to introduce the students of Unionville High School and their presentation, which is going to be on a comprehensive evaluation of toxic elements in fast fashion. All right, students, I'm going to spotlight you, and you guys can take it away.
Right. Well, hello and welcome to our presentation on a comprehensive evaluation of toxic elements in fast fashion. We are Team UHS, and thank you for listening to our presentation. So a little bit about ourselves. So we are a team of grade 10 to 12 students from Unionville High School, located in Markham, Ontario. We are all united with a love for science and research. This research was completed in collaboration with Georgina Tu, Joshua Zhang, Yifan Zhang, Tony Dong, Jadonti Seth, Neil Karkani, Ramin Zhang, Emma Lee, Tiffany Mo, Candy Yang, and myself, Armin Gistio. We'd especially like to thank our supervisor, Mr. Chan, for his expertise and support on this project.
To start off, we submit to two categories, one being fast fashion and heavy metals. Fast fashion is the production of clothing and the consumption of clothing to meet the demands of the latest fashion trends. Fast fashion clothing is regularly quickly manufactured. There has been increasing concerns over sustainability and ethical production practices, as heavy metals are often found in fast fashion clothing. Heavy metals are metallic elements with high atomic weights. These elements are toxic to humans, and large amounts of long exposure leads to dense molecular structures. One of the main reasons to conduct this research is for public health, especially in regards to pregnant women and young children. It is important to the public, especially pregnant women and young infants. It is important that fast fashion is a hazard to their own personal health. Another reason this is important is due to environmental concerns. When we studied heavy metal concentrations in the residue of our laundry, there is wastewater that has an impact on our ecosystems around us. These two significant problems is why we researched, and our research is incredibly important. The production and disposal of these clothes may lead to pollution to water and soil. There's a lot to learn from this research project.
So using the topic of fast fashion and heavy metals, we wanted to create a question that focuses on the concentration of heavy metals within fast fashion clothing items. More specifically, how we wanted to focus on how dye and material type can affect heavy metal concentrations, how washing fast fashion items affects the wastewater products, and as well how temperature affects the concentration of heavy metals. Using these factors, we were able to devise a question that answers three things. What levels of heavy metals, including cadmium, lead, and mercury, are present in the clothes and washing water from the clothes made from fast fashion brands? Does dye or material type affect the levels of heavy metals present in the washing water? And as well, does the temperature of the water affect the levels of heavy metals present in washing water? So with this question, we were able to create a hypothesis that states fast fashion poses a significant threat on heavy metals and safety. Fast fashion items we choose to investigate will contain traces of cadmium, mercury, and lead. These traces are transmittable to water, specifically affecting us when we wash our clothes. Therefore, the wastewater product resulting from washing these items will contain heavy metals. Washing methods, such as temperature and detergent usage, affects the heavy metals present in clothing. So there are a couple of things that we knew prior to actually doing the examples. We think some things that we knew that were clothing that is more vibrant and contains higher pigments is more likely to contain heavy metals. Clothing that is red, yellow, and blue, according to research done by Cost of Your Jeans, are more likely to contain mercury, cadmium, and lead. As well, another study done by Cost of Your Jeans in 2016 shows that cheaper clothing is more likely to contain heavy metals due to the unsafe working conditions of its production. This is due to the fact that fast fashion companies are able to make profit due to the often cheap and dangerous dyeing methods. And as well, clothing that is made up of materials such as PU leather, spandex, or denim are more likely to contain heavy metals due to the cheap production costs and unsafe productions of these materials, as shown by a study by Toxic Free Future in 2013. So some things that we wanted to consider during the sample selection were that the fast fashion item selections are to contain heavy metals, more specifically mercury, lead, and cadmium. The samples with saturated dyes such as red, yellow, and blue are more likely to yield results being mercury, lead, or cadmium. Samples that were inexpensive and unusually cheap are more likely to yield results. Samples that were made up of PU leather, plastic blends, and denims are also more likely to yield results. And we wanted to make sure to choose samples based on this hypothesis. So we'll walk you through a couple of the samples now. Sample one is a women's red top. Its material is PU leather with a polyurethane coating, and its color is bright red. Sample two are a pair of maternity leggings. The material is fabric with a 95% polyester, 5% elastane blend, and the color is maroon. Sample three is a children's leather jacket. Its material is PU leather, which are 55% polyester and 45% polyurethane blend. The color is a dusky blue. And sample four are maternity jeans. The material is denim with an 85% cotton, 13% polyester, and 2% elastane blend. And the color is a medium wash. Sample five are a pair of children's swimming pants. The material is 82% polyester and 18% elastane. The color is black with various patterns on it. And sample six are a pair of children's jeans. The material is denim with a 93% cotton, 4% polyester, and 3% viscose blend. And the color is medium wash.
Okay, so before we talk about the sample preparation, I'm going to talk about our sample code. So first we have S, which represents the state, which is either solid or liquid. We have K, which represents the sample number between 1 to 6. Then we have C, which represents the washing methods. These washing methods are C for control, H for hot, L for cold, and W for pure water, and D for detergent. So now for our sample preparation. So when we were cutting our samples, we cut 5 2 centimeter by 2 centimeter squares for each sample. The control samples were unchanged for both solid and liquid. The cold water with pure water was the cold water with pure water. We first put a magnetic stir bar inside of a beaker. We then filled that beaker up with 30 milliliters of pure water. We then surrounded that beaker in an ice bath, measuring the temperature to be around 12 degrees Celsius. Our original predictions would have been 0, but we compromised at 12 degrees Celsius. And then we placed the beaker on a plate and we turned it on, spinning it for about 45 minutes for each sample. For hot and pure water samples, we used the same process, just substituting the ice bath with a water bath. And then for the cold and detergent sample, we use the same process as the cold and pure water sample, just removing just adding 1 milliliter of detergent about. And for the hot and detergent sample, we use the same procedure as the hot and pure water sample, just adding 1 milliliter of detergent and removing the ice. So after completion, all solid samples were placed in a paper towel by the windowsill to dry naturally, and all liquid samples remained in their beaker, where they would also evaporate naturally to about 2 milliliters and were collected using the vials provided by CLS.
Now I'm going to be talking about the XRF technique that we use to analyze our samples. So XRF basically means an X-ray fluorescence spectroscopy, which determines the elemental composition of the material. So how it works is it measures the fluorescence of a material or sample, which is excited by a primary X-ray source. So as you can see at the bottom of the slide, this is our XRF scan data for our control samples. And it's basically a line graph with the y-axis and the x-axis. The y-axis has the photon count, which tells you the concentration of the element. And then the x-axis is the energy levels, which tells you the indication of an element. On the top right corner, you can see there's a legend, and this says which photon curve is which sample. So as you can see, each photon curve has different colors to it. And then you have vertical lines going through the photon curves, which are element identifiers, and they tell you which element is where. So as you can see, the green line is copper, and then the purple line is zinc. Now moving on, so how we analyzed our data was that we had to analyze our water and material samples to identify specific elements, which were mercury, lead, and cadmium. And we had to identify them, so we used a resource from CLS, or the Canadian Light Source, and they provided us with the XRF reference sheet. And how this reference sheet works, it's on the right side of the slide, and it has 4 columns to it. It has the name of the element, the name of the symbol of the element, and then large peaks and small peaks. And under large peak and small peak, there are a few numbers, and this is the photon count for each one. So for example, if you see a large peak with around 4,510 photon counts, then you can say that this would be titanium. And this is the method that we use to identify the rest of the elements. And just like that, we identified all the elements throughout all the samples. And after that, we discovered the different elements. We had to make sure and confirm that these were accurate, since cross-contamination is possible through maybe scissors or our hands that we had used.
So all samples do not contain heavy metals like lead, mercury, and cadmium. But copper, zinc, and iron do appear, but they appear randomly, so we're unsure on the conclusion. This rarity scan is an example to show these 3 elements. Also, we know the control water group already has iron, copper, and zinc. To prove there are no mercury, lead, and cadmium, the denim jeans example shows no peaks corresponding to these elements. The same thing also happened to other clothing samples.
So even though we didn't end up finding any toxic heavy metals like lead, we did find some interesting patterns for other elements, and one of them being calcium. So we started by analyzing the amount of calcium in each control sample and notice the pattern. So as you can see on the graph here, for the two lighter samples, 1 and 3, the left top and the left jacket, they contain a huge amount of calcium measured by the photon count at the alpha peak, which is the larger peak, and that's significantly higher than the other samples. And then there's the 4 and 6, the two denim samples. They also contain some calciums, but significantly lower than the lighter ones, but still much higher than the fabric ones, 2 and 5, which is like 1,000 photon counts versus 3,000 or 5,000 photon counts. And from this pattern, we decided to do further analysis based on the material of the clothing. To start with, we did analysis on the leather samples. So we basically do the analysis for the control group and the four washing methods: hot water, low water, hot detergent, low detergent combined. So for both leather samples, the low detergent one after washing has a significant increase in the amount of calcium compared to the control group, whereas the other washing methods doesn't show a clear pattern and are very close to the control sample. For the denim samples, they also show a consistent pattern that pretty much all the samples show the increase in the amount of calcium after you wash it, and this is especially obvious when you wash it with detergent. So as you can see on this graph here, the bottom one, the blue curve is the control one, which is the lowest, and these two on the top, they are the hot detergent and the low detergent. And the one this side, number 6, the other blue denim jeans, show a similar pattern, that the one on the middle is the control one, and the one with detergent are still two of the highest. The only exception is the low water one, but because how other samples are showing the pattern, this is the only exception. This may likely to be an random error. And finally, there's the fabric samples, which doesn't show any clear pattern, as you can see on these two graphs. And it seems like after washing doesn't cause a difference in the amount of calcium for those samples. So then we analyze the source of calciums. For the leather ones, it most likely comes from the calcium carbonate during the production process. And for the denim ones and the fabric ones, they are most likely come from the water, because we found some other sources of calcium here on the second half, but none of them matches the materials we used. And also there's calcium in the detergent we used, which contributes to the increase of calcium after you wash it with detergent. So in conclusion, we concluded that different materials have different capabilities to receive calcium from water and detergent. For polyester leather, or PU leather for short, they are most likely to absorb calcium when washed in cold water and with detergent. For denim ones, they are likely to absorb calcium when you wash it, but more obviously when you wash it with detergent. And for the fabric ones, it doesn't tend to absorb calcium regardless how you wash it. And this difference, interestingly, also matches the previous finding that the denim ones initially contains more calcium in fabric, which also, as we analyzed, come from the washing process.
So we also found some interesting patterns in titanium. Titanium is an element that is found across all 6 samples, and they are present in pretty abundant amounts. As shown in these two graphs, you can see that titanium has pretty high peaks compared to the other peaks in the sample, and that is true across all 6 products. They are not always the highest, like the most abundant elements, but they're among the highest ones. So we suspect that titanium is present in the form of titanium dioxide, which is a universal whitening and brightening agent, and it's extensively used across industry, including plastic, paper, rubber, textiles, and even food industry, according to the Handbook of Natural Dyes and Pigments, published in 2014. So titanium dioxide is skin-friendly, according to a study in 2015. So if it's only present in the clothes, it will be all right.
The study shows that it doesn't permeate through neither intact or damaged skins. They only stay at the very surface, which is the epidermis part, and the sternum corneum part. These are the very surface of our skin. And it barely has any cytotoxic effects. In fact, it only has those effects when it comes in very high concentration and for a very long-term exposure. However, another study in 2016 pointed out the environmental concern that even at low concentration, titanium dioxide nanoparticles can impact the denitrification enzyme activity, which is over here. And thus it will impact the whole nitrogen cycle and impact the bacterial structure, bacterial community structure in the soil. Because of those environmental concerns, let's zoom into the titanium part of the graph and take a closer look. Here, I still chose sample 2, the red fabric legging, and sample 3, the blue leather jacket, as our samples, but similar patterns are found across all 6 samples. So here, when I labeled it out, you can see that the peak here and here consists of only solid samples, and all solid samples have this peak, whereas the liquid samples are at the bottom over here. So it shows that when it comes in terms of solid versus liquid, titanium mostly remain on the solid samples and are not washed into the liquid samples. It almost contains no titanium. If we zoom into the liquid and the liquid control groups, again, the same samples, but the same pattern is found across all 6, we can see that they have about 200 photon counts, which is insignificant because across all the graphs, it has a minimum of about 200 photon counts everywhere. And another important thing to know is that the liquid samples are mixed with the control groups. This means that the liquid washing water, the water after we wash the samples in, has about the same level of titanium as the control group. It means that insignificant amount of titanium is washed off. This is both based on both the solid and the liquid samples. And since it's mixed with the control group, it also supports the idea that insignificant titanium is washed off. This result relieves the environmental concerns. And then also after we found out, we did some research, and this confirms a previous study's similar conclusion that is published in 2012. So if we look at these 2 graphs, it's a bit hard to identify how the washing methods actually impact the wash off of titanium. Although it's insignificant, it is still some amount. As we see, I organized it into a graph, and in these graphs, you can see that when we wash with low temperature and with detergent, titanium has the most amount. And in fact, among the 6 samples, we have 4 where the low temperature and with detergent are is the highest. And for the other 2, like sample 2, for example, it's still among the highest, although it's not the highest. So our observation is that water with detergent at low temperature seems to have the most remain of titanium on the solid sample, but we don't know why, and further research is needed. And the control cloth may have more or less titanium remains. Here you can see that sometimes it's more than the samples, sometimes it's less than the samples. But we are not sure why that happens. It might be due to some titanium in the water or in the detergent, but future research is needed to figure out exactly why. So next section, we're going to move on to bromine.
So another element we found interesting from our samples is bromine. And among the 6 samples we investigated on, 4 of them, including the red fabric legging, the blue leather jacket, and the 2 blue denim jeans, contain a significant amount of bromine, which in XRF scan results in a photon count of more than 5,000. And taking a closer look at these 4 samples and compare the amount of bromine before and after washing, we found that the denim jeans, as well as the blue leather jacket, has a lower concentration or photon count of bromine after any types of washing methods compared to the unwashed ones. And showing a pattern that bromine is constantly washed out from all the 3 samples. And on the left of here is the graph. And we can see that this blue curve indicates the original untouched piece. And you can see it's significantly higher than the other than the curves with other colors, which are the closed pieces washed with different methods. And also note that this red fabric legging does not follow the same trends as these three. Well, anyways, taking a look at the pattern of the three clothes, the leather jackets as well as the two denim jeans, we did some numerical calculations around the three samples, and by comparing basically the folding counts of the untouched piece as well as those we washed. And on average, we found that about 13% of the bromine is washed out from the closed pieces, which is a pretty significant amount of changes. However, this pattern is not further supported by the liquid samples we collected after washing, because these bromine only exist in minimum concentration with a folding count less than 2,000. You can see from the graphs here, and there is not a clear pattern of increasing bromine after washing inside these liquid samples as well. So yeah, I mean, this may caused by some potential sample collection issues, but still further researches on these samples could be done to verify our pattern. And well, nevertheless, many speciation of bromine could be hazard, and the leaching bromine may comes from different compounds, and thus may have different effect on environment as well as human beings. And that's why it is important to determine where exactly this bromine comes from. And our first hypothesis is that this bromine may comes from brominated flame retardants, the BFRs, such as the Bangkok BDEs or the TBBPA. They are often used in polyester products like leathers and denims to basically prevent fire from spreading. And often poor qualities in production procedures may cause BFRs to fix unstably on clothes, and thus makes it easier to wash out from the clothes pieces. And according to many past researchers, BFRs can negatively impact the environment when released, and can contaminate the air, soil, and water. Well, another hypothesis we have is that bromine may comes from type of blue dye named bromo indigo, also known as bad blue 5, used in denim dyeing. And this is a more plausible explanation, as the three samples we found these patterns in are all in blue colors, while the other three samples that did not show the pattern are in different colors. And researchers also showed that this bad dye only adhere to the outer layer of coating, and therefore can be washed out if the dyeing process is not properly done. And in fact, in our procedure of washing, the denim jeans, so sample number 4 and number 6, shows that the blue color is washed off very evidently. As you can see from here in the picture, that the waters after washing are pretty blue in color, while in comparison other samples after washing, the water is pretty much transparent. And well, bromo indigo is basically an environmental concern if present in a large quantity, and the dissociated bromine ion can be very dangerous to aquatic organisms, and it can also cause allergies and even some chronic diseases for human beings. Also, the production of bromo indigo is also an environmental concern, as some of the chemicals used in this process, such as hydrose and sodium hydroxide, are not that environmentally friendly. Well, again, these are just some hypothetical sources and impacts of bromine in fast fashion clothes, and further research is still required to identify the actual source of this bromine, or verify our hypothesis if possible. And Also, quantitative analysis on bromine concentration will be really helpful to determine the actual environmental impact of these clothes.
So in conclusion, the fast fashion clothes investigated in our study were found to be free of heavy metals, such as chromium, mercury, and lead. However, we did identify the presence of other chemicals, including calcium, titanium, and bromine, which have the potential to pose environmental concerns. While certain patterns have been observed in the outcomes concerning temperature and detergent usage variations, there is a lack of definitive patterns for other factors. Consequently, no conclusive results have been obtained regarding the influence of washing methods on the extent of leaching into washing water. Our findings indicate that fast fashion clothes do not exhibit significant issues concerning the presence of heavy metals in the products. Therefore, individuals can rest assured and not be overly concerned about this aspect.
Reflection and limitation. We found that we're unable to maintain at hot temperature. So this is our thought at first that we have three temperatures. One is cold temperature at 12 degrees Celsius, and one is 25 degrees Celsius, and the hottest one is 50 degrees Celsius. And as you can see, this is our magnetic platform. We are unable to heat it to maintain the hot temperature. So we changed to low temperature and room temperature, which is at 0 degrees Celsius and 20 degrees Celsius. For the cold temperature one, we can add ice into the beaker to maintain the cold temperature. Copper and zinc are normally high due to the improper use of tweezers and scissors. So this is an example of our clothes piece, which is sample number 2, the red one, that some contain really high proton counts of copper and zinc. This appeared in some other sample as well, but we are unable to find any pattern or similarity from it. So we assume this is because we didn't use the tweezers and scissors properly. Water come from school tap water might have slight difference because you can see here the room temperature. The room temperature, the orange one, and the red one, which is the cold temperature water, have 500 photon counts difference for the ion. So this might due to the tap water difference because we did it across different days. There might be some heavy metal stick to the bottom of the beaker that we are unable to collect as well. So at first we have two options for the X-ray. One is stains and the other one is XRF, and we choose XRF at the end. XRF and stains can be performed in air and vacuum. Two-dimensional mapping with sub-millimeters resolution can be performed in air on large samples. The another choice we can have, which is stains, is a subset of XAS, defined as the analysis of the local electronic structure of an atom. XAS provides information on chemical and electronic environment of specific elements, and it can be used to identify different chemical species present in the sample. And this leads to our future research.
So for future research, we think that it will be very useful to use zinc to identify the exact species the elements are present in. For example, for bromine, we're not sure which dye it comes from. We had some hypothesis, but we cannot figure out which one it exactly came from. If we can figure out the compound that it came from, it will be very easy to figure out the exact source that comes from. Also, for titanium, we're discussing it because we suspect that it comes in the form of titanium dioxide, but this is not 100% sure. If we can use zinc in the future, we can confirm the compound and maybe do more research and deepen our understanding. We could also further investigate the effect of different washing methods. We found some patterns in regards to different elements with different textiles, but we cannot explain how and why these patterns form. If we can use more quantitative methods in the future, for example, some can use temperature or the amount of detergent as independent variables, and the photon counts that the element has as the dependent variable, we can try to use quantitative analysis to figure out a relationship or a function between these two variables. We could also lastly further explore the impact of different types of textiles. For example, for calcium, it is found that leather clothes have similar patterns. Denim clothes have similar patterns, and then fabric clothes have similar patterns, but the patterns are different when it comes to different types of textiles. So if further research can determine how certain textiles contribute to more or less elements deposit on the samples than others, it will be very good to help our understanding in this topic. And these are the references that we used in our research project and our presentation. For further background information in detail, you can take a look at this, and I'll tell you more in detailed background information. And finally, we would like to acknowledge and thank a lot of help that comes from various people involved in this study.
We want to thank all the CLI staffs and professors involved in our project, Ms. Tracy Walker, Ms. Dallas Pelly, Ms. Mercedes Bui, Dr. Jay Dines, and Dr. David Muir. And thank you so much for your guidance, help, and support throughout our project. And we also want to thank Mr. Chen and Ms. Mantello for their time and effort in supervising our team meetings throughout the 1.5 years. And lastly, we want to thank all the researchers who used to be with us and contribute to our project. And thank you all for your time and efforts. And now let's proceed to the Q&A section.
All right, any questions from anyone? You can unmute yourself or type it in the chat or raise your hand on Zoom. So these are kind of, anyone have any science questions for the crew? Just giving people a minute if they thought of anything or they're still thinking. All right, so I don't have any science questions because I've been along with you guys for this whole process, but I do have a question, not about your science, but about more your experience. And so I'd like each of the students to come up to the screen in a minute here and share what your experience as a high school student, right? You got this opportunity to use the facility of Canadian Light Source. That's a pretty rare opportunity. And I'd like for each of you to share with us something that you learned that you will take with you as you continue in high school, in university, or onto a career. Right? We can assume that you guys learned a little bit about spectroscopy. You learned about the elements you researched, things like that. But was there some things that were personal to you that you learned that you think will help you along the way here in your future? So whoever's ready to come up to the computer and share with us what you learned. All 11 of you.
I want to start with what I've learned. So other than learning more about the scientific research process, one thing about scientific research I learned is this process always comes with unexpected things. And so one example was what we initially expect us to find some heavy metals and found a lot of reasons, but then we end up not finding heavy metals, but instead we found some other metals as well as other interesting element patterns. And I would like to take this in my future pathways to always not be afraid of the unexpected, but to learn from those things. Just like how we learned from those calcium, titanium, and bromine patterns. Yeah, that's basically what I want. And thank you for this opportunity.
Thanks, Yifeng. All right, who's next?
Okay, so throughout this experience and with the research team, I learned that even though you may not be able to find exactly what we were looking for, because we were looking for specific elements such as lead and mercury and cadmium in our samples and our materials of the clothing. But if we're not able to find that, it's okay, because we found so many other things and more results that we weren't expecting, and we were able to learn so much even without actually getting the results that we wanted. And I feel like that could also really help in the future, as throughout life you're not going to be able to find exactly what you want, but you can still learn a lot throughout that experience.
Thank you.
I'll go next. So yeah, so first I will really agree with what Yifeng just said. So I really learned that scientific research is a process that is full of unexpected discoveries and stuff like that. And I will really take that into my future research and education in post-secondary. And also something I really learned from this experience is basically just how a scientific research will be conducted. So we start from creating a proposal, and then we design our experiment procedure and implement those. Then we gather our data and do analysis on that, and eventually we are here to make a scientific presentation on our findings. And along the way we work with so many researchers here with a very big team, and I also really learned about how to communicate and coordinate with so many excellent researchers here. And yeah, that's something I learned from this experience.
That's wonderful. Thank you.
For me, I think one of the things that I learned was the value of patience in a scientific project, just because we started the preparation for this almost a year and a half ago. And at that point we had literally nothing, and it's taken a lot of work to get to where we are now, and a lot of time and dedication. And I think that in the future, even if you think that you have nothing, just be patient and just work hard, and eventually you will have something.
Thanks, Neil.
One specific thing that I learned about was just more specifically about chemistry. During a lot of the research process of this experiment, we got to learn a lot about different elements, properties, and that was a really interesting experience. And considering that, this was a year and a half ago, we didn't really have I didn't have a lot of general experience about, the broad subject of chemistry. It was a lot of fun to learn.
Great.
I learned that the improper use and unclean of the equipment could actually introduce contaminants and affect our data. So resulting in unsafe data. So what I learned is even during the experiment, we still wrapped the scissors and tweezers with tape. We still need to be careful and prevent this.
Okay, so I'm going to say that I thought I was closing this off, but I'm not. So I would like to say something about drawing conclusions and finding out the actual thing behind it. So for our project, although we had some expected values that we didn't find, and we found some unexpected results, and during this process, we were pretty frustrated that we couldn't get the exact reason why this pattern show up as this is, why this goes this way, not that way. We want to figure it out, but it is not in our reach in the short term. So I think what I learned is that we need to take it step by step instead of just taking a very big step, wanting to go to the end. It is always a process of going one step and another. It's a very long journey that you need to go on, both for research case and in terms of the knowledge of humankind, I would say. If you always try to go one, and then the people come after you or yourself in the future will take it one step forward and one step forward. It's not always a one-step process that can take you directly to the destination. There's no destination, there's no end. So you have to take one step and keep going forward. And that's what I learned from it. Thank you.
That was very beautiful. That, you know, that image of walking forward and, you know, you haven't quite come to the end, but someone else might be able to take it that much further. I think there's a couple more of you, right?
What I've learned is that I was pretty nervous that I feel like I might not have much to say and like not know much of it, but I think that after like looking at like a lot of the data, that even though we didn't find exactly what we wanted to, but the element that we want, we still find some other elements, but at least we know that it's not too dangerous.
All right, the last one. I've been counting, but I'm not sure how many we're at.
Yes, I learned a lot about like the research process and like different data analysis and working together.
Yay!
Yes, that working together piece is very important. That was all 11 of you.
Yeah, that's it. I think that's all.
Perfect. All right, well, thank you guys. I know you've worked really hard over the last couple of months and it really shows. That was a really good presentation, so great job. I can definitely say you guys have taught me so much during my work with your team. Like I said earlier, this wasn't kind of my first go around with the students on the Beamline group. And so as I was navigating and, you know, learning the science and navigating my way through, we lost Beam and had to switch to doing things virtually. And, you know, our plan hadn't gone as we originally planned with the samples and everything. It's been a really big roller coaster ride. And I know lots of you guys have felt that too, students. That I've been feeling that experience with you throughout as well. But I got to learn so much about how students communicate together with each other. And it was really awesome to see you guys, you know, figure out your data and see that growth from your day one of looking at your data until the presentation today. It's really awesome. You guys did some really great work. So I learned a lot from you students, so thank you. Now, I don't want to let your mentors off the hook either. So I'd like to invite both Jeffrey, Mr. Chan, and Jay Dines to also comment on what you two have learned over the course of the last few months. So whoever wants to go first.
I'll start first, I guess.
Thanks.
So, I didn't think I was gonna be on camera. I guess for me, I did this type of research like, you know, back at university. So for me, it was really hard to, like, at the beginning, it was really hard to stand back and do it sort of myself. Because, you know, my students are ranging from grade 10 to grade 12, so they don't have a lot of experience. So it was just watching that process at work
and really sort of holding myself back and not telling them what to do in order to get the like, in my opinion, the most optimal results. So that part is for me, but it was also, you know, not just the scientific part, I guess, but also I really learned about paperwork. So that was a lot of fun. But yeah, like leading them and just watching them, like, and not really participating, but at the same time participating, because, like, you know, you're telling them, you know, advising them to be patient, to keep at it, sort of, even though, again, we didn't get the results that we were initially hoping for, but really working with them through those steps and you know, finding answers to other things that were popping up along the way. So that was quite fun for me. Yeah.
And Jay, if you're there, can you?
I'm here.
Okay, go ahead.
Yeah. Well, I've worked with about 10 other groups, and this was very frustrating for me because the students didn't come to the synchrotron. All other groups I've worked with, the students come to the synchrotron. So the interaction with the students was really missed, and it was hard to help them do their research when you weren't really involved. Like, even collecting the data, I wasn't there, so it was hard. And so I found that frustrating, but overall I thought they did very good and under the circumstances that they had to go under. It's too bad that didn't get to come. Maybe next year their group comes, it'll be better. I think that's all I have to say.
Perfect. Thank you for sharing. Yeah, and thanks everyone for sharing. We have one last note from Mr. Dallas Pelly, and then we'll say our goodbye. So Dallas, you may go ahead.
Can you hear me? Hello.
We can hear you.
Hey, I just want to say thank you to Unionville. I jumped on here. I'm actually on holidays, but I loved you guys so much that I just thought I'd jump on here and just say how amazed I was by your progress, by your energy and enthusiasm, and for finishing well. I know it's not easy going into summer and thinking about this, but we really appreciate you guys taking it all the way. And yeah, like when Mercedes and I, like Mercedes literally shed tears when we found out you guys couldn't come. But I think that through that and through the challenges, we were able to kind of make some meaning from an unfortunate circumstance. And I tell you, like, going through that data with you, I was blown away at how quickly you were making the connections you were making. And, you know, when we were doing group work on Zoom and all of that, you guys have a bright future. And I was so proud to have worked with all of you. And so, yeah, I look forward to seeing some of you at some point. But yeah, I just want to say thank you and hi, Miigwech. And yeah, just wish you all nothing but the best.
Thank you.
Thank you. Thank you.
And that wraps up another awesome Students on the Beamline presentation. So thanks, students. Thank you all of our guests on Zoom and our live stream watchers for coming. Have a great rest of your day, everybody, and take care.
Thank you.
Thank you.